Yes. I think you are able to see the screen, right?
Yes, sir. Visible.
Okay, fine. So anyway, so last class, so we have started, you see the two-dimensional random variables we have discussed. So two-dimensional, of course, you can extend it to even multi-dimensional also. So this also we have seen, like, the joint densities, okay? So P, X, Y, X comma Y, the joint distributions and other things also we have seen. And then finally say, we have started this functions of random variables. Okay. So in the functions of random variables, say, so what we have said was, so we have x, say, which is a random variable, and we know it's a probability density function or it's a probability distribution function, say. Now we have y, which is a function of, the x. So now what will be the probability density function, the distribution function for this y? So this was a question, you see, we were trying to answer in our last class, okay? So now here, so it is very simple as already we have said. So, the random variables, say your x and y, they are linked through this, this type of function. So we have some type of a graph or whatever, So this is my y is equal to g of x, say. Okay, so this is my relation between two random variables, that is x and y. Now I know the density function for x. Okay, so let us say it is a normal or some type of a density function. Okay, so px of x. So now we have to find out, you see, the probability density function for y. Okay, so this is something, it may be, you see, something like this. Okay, so this we have to find out. So on the y-axis, you see, we have this py of y. So, and of course, this is my y-axis, and this is my x-axis actual. Okay, so now what we said was, the density function means, so if I want to find out the probability, say y lies from, this range, say. So what is the probability that y will range from y1 to y2? So this if I want to find out, okay, y1 less than y less than or equal to y2. So this if I am trying to find out, but I don't know the density function of y. So but yx I know and the relationship I know. So what we have to do is you project this onto this probability density function for x. Okay, so like last class we told, so you project like this. So this type of a projection you can do these numbers, say. So it is as good as saying that, so this is my x, so you just project all these things to my probability density function for x. So now, you take these areas, say. So you may have two intersections or one intersection, or I don't know, depending on the number of the roots. So now it is as good as saying that, you find out the area, say, in this portion. Okay. So now this is a portion which is, you try to find out, say. So now, so the area under y1 to y2, say. So this is equal to just a sum of, this area plus this area plus this area plus this area. So how many intersections will be there? How many roots will be there? So it depends on your g of x. Okay. So if it is a straight line, say. So obviously, if it was a straight line, something like this. Okay. So this is a relationship between y and x, say. Okay. So now how many projections will be there for a straight line? No. How many roots will be there? Yeah, see, if there is only a straight line, say, okay, so like, I have y is equal to x. So some line I have. So this is my probability density function, okay, of y, and this is my probability density function for x, say. If I want to find out the area, that is y less than or equal to this one. So if I, now what we have to do, we have to project it onto the, the x-axis, okay. So this is my y is equal to g of x line, say. So now how many intersections will be there? So if we see here, so it can have only one, right? So obviously, so it is as good as telling, so this area and this area, say, both of them are same itself. Okay, so mathematically, so this we expressed in the last class. So we said py of y, say, is px, okay, of this function, v of y, and multiplied by, you see, v dash of y. So this is a fundamental, the expression actual. Okay, so where you can use it and to find out, these functions of random variable. So last class, we have done some examples also. Okay, so these are very, the important kind of thing. Now let us see one more very important transformation. Okay, so let us say y is equal to a sine x plus theta. Okay, so this is a transformation. Now a and theta are constants for the time being. Okay, they are not random variable, they are just constants. Okay, there is only one number. X is random. Okay, and then so and it has its probability density function. So px of x. Okay, and now this is known to us. So this is known to us. Now I have to find out what will be the probability density function of y. Okay, so this we have to estimate actually. And y and x are related through this sinusoidal, the relation. But of course, this sinusoidal relation, the amplitude and the theta, they are constant, but x is inside. Y is equal to sine x. And now how do we calculate this one? How many times the intersections will be there? How many roots will be there? See, y is equal to a sine x plus theta, say. So if you try to plot this, okay. Now how it will look like? So y is equal to, so this is my x-axis. This is my, you see, this y-axis is here, say. Now how does this function will look like? Y is equal to a sine x plus theta. So you have seen, right, the sinusoidal function. So, it will be, you see, oscillating basically. And sinusoid, it goes from minus infinity to plus infinity. So it will be oscillating like this, okay. And now we have to find out the probability density function for y, okay. So now y, you see, so y maybe you followed it, some, this portion will be there. And then x say, so I know the probability density function for x, something like this. Now we have to find out, probability of y itself. So of course you can directly use this expression itself. Okay, like you see, we have to find out v of y. So we have said y is some u of x, say, and x is, you see, v of y. You have to write the inverse relationship. So y is a sine x plus theta, say. So now if we reverse this side, okay, so x will be sine inverse of y by a minus theta. So this is our v of y. Okay, so now you can substitute in this expression and you can find out. So now p of y say, so this will be, as already we have said, so px. Okay, so you have to substitute px of v of y and multiplied by v dash of y. So the derivative has to be found out actually, and your v of y is this expression. So now you calculate and tell me what do we get. Now what is the derivative? What is v dash y? That is, you find out the derivative of sine inverse of x. What do we get? See, what is the derivative of sine inverse, okay, of x? What's the derivative of sine inverse of the y?
1 by root of 1 minus y
So
square.
all of you are there, right? Yes. So now what is the derivative? You know, no? That is 1 by some square root will be there.
Root of, yes, sir.
So py of y will be, see, 1 by root of a square minus y square. So this is v dash y. Okay. So now we have to multiply by this px also. So now this px say. See, now how many roots are possible? See, like now if I want to find out this area, okay, that is a probability of y. What is the probability that y1 less than y less than or equal to y2? Okay, so now how many roots are possible, because it is of sinusoidal x, say. So now what happens? How many roots? If I project it onto the x-axis, what happens? Yeah, what happens? How many roots will be there? How many roots are there for sine inverse? The sinusoidal functions say. How many roots are possible? So you can see, so this one combination is there, you followed. So you have the small set will be there. So this area, and then because sine has so many roots, right? So this area, all these roots has to be found out actually. What is the value of this root and what is the value of that function has to be found out. So this we can write this as n is equal to minus infinity to plus infinity. So infinite roots are possible. xn, where xn are the roots basically. Okay, that many will be there. So you have to sum up. So this area, say this is equal to this area plus this area plus this area plus this area, like that. You have to conclude from you see the minus infinity to plus infinity. So that many roots are possible actually. Okay. Now for the time being, say, so if I say that this p of x, okay, is uniform distribution, say. But one more thing here is this problem, say, okay, now x lies from minus infinity to plus infinity, okay, but y lies from where to where in this transformation. Y also will go from minus infinity to plus infinity, or where y will lie from? Yeah, x goes from minus infinity to infinity, the sample space for x. What will be the sample space for y?
Minus a to a.
Minus a to a. You followed, because y is a sine x plus theta, and we all know, right, sinusoidal, say it lies from minus plus 1 to minus 1, and of course the amplitude is a, so y is bounded but x is unbounded basically. Okay, so this you have to remember. So this y lies from, you see, minus of course a to plus a. Okay, and now let us say px is, let us say I will give you px as a uniform distribution, and it lies from minus pi x less than pi. So now I am bounding my y. So let us say my x value is like this, the probability density function. Okay, so this is minus pi, and of course the value is 1 by 2 pi. Now what is the area under this curve? Now, so this is my x. Okay, this is my density function for x. Now, what is the area under this curve? This rectangle.
1.
It is 1. Okay, because what should be the how do you verify whether the probability density is correct or not? What is its basic property? See, if some density function is given to you, say, how do you check whether it is correct or not? What is the first check you do?
Area under
Area
its
under
domain
the
should be equal to 1.
Area under the curve has to be 1 actual. Okay, and now in this problem, say, now previously we have said px of x was infinity to infinity, and now we are restricting x from minus pi to pi. So when x is more than pi, or x is this one's probability is almost 0 itself. And now what will be py of y? So now you tell me 1 by root of a square minus y square. So how many roots are possible from minus pi to pi? So if you plot, this y and x, say, okay, so y is a sine, you see, x plus theta, but only condition is now x lies from minus pi to pi only. It doesn't go from minus infinity to plus infinity. You followed. So how many roots will be there? Now, so if you substitute, say, you can find out. Okay, so this will be something, maybe one cycle or whatever this itself followed. So something like this, you will be having this much only, that is from, you see, minus pi to some pi. So this is the limit up, otherwise it is 0. So now when you try to find out the y, say, of course y the maximum as already we said. So although x may be this one, but minus pi to pi, but y will always lie between minus a to plus a actual. So now if I want to find out this area under this curve, say, so how many roots are possible? So how many times it will intersect basically? This is my px of x. Okay. So in this region, say, how many roots are possible? So if you see this, how many times it is intersecting this axis?
One time.
Look at the figure.
2 times.
2 times. That is one here, another here. So one root somewhere here it will be there, and you will be having another root also. You followed. So 2 roots, will be there. But you can find out the roots also. But without roots also, we can easily solve. And now, what is the probability value at this root? What is at this first root? Say, what is the value of probability density function? Now, what is the value? So at the first root, what is the value of px of x1? See, it is a uniform random variable. Okay, whatever value, suppose if x is 0, say, what is the value of px of 0? Now, what are the values in that small range? Okay, so what is the value? Now, what is the probability of x between minus pi to pi? What is the value?
1 by 2 pi.
1 by 2 pi, it is constant, right? Whatever may be your roots, it is 1 by 2 pi only. You can find out the roots, but in this problem you followed, right? Not two roots will be there. So the value is only important for us. So 1 by 2 pi, 1 by 2 pi. You followed. So this is our probability density function, you see, of y. And if you try to plot this function, say, how does it look like actual? Okay. So if you try to plot this in MATLAB or whatever, Excel or this one, so it looks like this. Okay. So y, py of y we are trying to find out. So the maximum value is minus plus or minus, you have this a minus a plus a. Okay. So this function say when that it is 0, when y is equal to 0, what will be the value? So this is my probability density function for y. So I can write this as 1 by pi or whatever. So 1 by pi root of a square minus y square. So this, if you try to plot it on the computer, say, okay. Now when y is equal to a, what is its value? When y is equal to a plus or minus a. Now what is the value? Substitute here. When y is equal to plus or minus a, what happens? It becomes
Infinity.
Infinity. When y is equal to 0, when y is 0, if you substitute y, it becomes
1 by a pi.
1 by a pi. Excellent. Okay, so now this is how you have to plot actual. Okay, so now this function, say this probability density function, if you try to plot it, it will be like this. So this is of course this value is 1 by a pi or whatever here. So and then you see you can find out the value at other places. So now your x is basically like this. Okay, so this is a probability density function of x, which was uniform random variable, and its value was equal to 1 by 2 pi, and it was varying from minus pi to pi. Now when you did this transformation, say a sine x plus theta or whatever, so what happened was your probability density function of y, say, because the transformation is not linear, no, it is a sinusoidal transformation. So now the probability density function of y became like this actually. You followed. So this is a very the important transformations actually. Okay, so variety of distributions comes from this transformation. If it is a linear transformation, so then the px and py may be same, but you see the distribution may not change. But if it is a nonlinear transformation, say, you can get variety of distributions. Okay, so this anyway, so this is how you see you have to interpret. Okay, so so this is a formula you have to use when you try to find out this transformation. But you have to know the physics also. So physically what you are doing is the relationship between y and x, say. So this will tell you how many roots are possible actually. Okay, so you plot it. Okay, y is equal to x square, whatever function is given to you, approximately you plot it, say. And now what we are trying to find out is probability density function of y. That is essentially you want to find out p of y less than y12 less than. So if you try to project it onto this plane, say, and then project it onto this one. So when you project this onto the function, you will get the roots basically. Okay. Now, once you know the roots, say, you find out the values at this root basically. So this will be done by given by this px of x. So then you have to sum up all these contributions. So if it is a linear mapping, say, then you may be having only one root. Okay. But if it is a non-linear mapping, y is equal to x square, like last class, we have seen, right? This also. See this one also. When it is x square, so this type of transformation, say, so the figure is something like this. So there may be, you may have contribution from both. So you have to add the area from this side, area from this side also. Suppose if there is only one root, say, so then you may have to do, it is maybe a linear kind of thing, only one root may be possible. So you have to be, so this is how, we calculate this transformations. Okay, the physics of this problem is, the physical meaning is essentially what you are doing is you are projecting, like your probability density function of y, you are projecting onto the probability density function of x through this transformation. Okay, but you have to find out how many roots based on the figure. So sinusoidal, they may have infinite roots also. Okay, so that is how things looks like. Anyway, so now let us say two functions say of random variable. It is a two-dimensional problem. Okay, and now this is also we use in even in our every time we do x and y say, let us say they are all random variables. Okay, and they are two-dimensional random variables. So you know their joint density, that is a pxy, or they you can know that the probability distribution also, the joint the distribution function, joint density function. Now two random variables are there. Now I have another random variable w, which is a function of x and y. Okay, then I have another random variable some z, which is also function of x and y. You followed? So both are getting a transform. Now the question what I ask is, so p z w say, what will be the density function of these random variables actually? Okay, so x and y. So whatever we did was one dimensional. Now we are extending it to two dimensions. So two random variables are there, and you know their joint density function or distribution function. Now we have another transformation. Okay, it may be linear or it may be non-linear also. Now I have to find out their joint density functions actually. So now so this can easily be found out by the same transformation. Okay, so same concept you can use, but the same expression. So whether I can use this expression itself here also? Yeah. So this was valid for one-dimensional data. Okay, so now this was valid for one-dimensional. Now what happens in two dimensions? Yeah. So 1D or 2D say the the method has to be same, but what happens so this is only one dimension. So now I have to do two dimensions. Okay, z w z comma w, and right hand side of course I will be having x y x comma y. Now what will happen to the derivative in 2D? See, in one dimension if it is a derivative, say in two dimensions what happens when there are two functions? What will be the derivative? See, the ordinary derivative when it goes to 2D, what happens?
Partial derivative.
It will be partial derivative. What do you call that expression? Say, what is the derivative in two dimensions? 2D or 3D or 4D or 5D say. Now what happens? The derivative, what do you call the derivative? You use in FEM everywhere, no? A parent element will be there, you followed. Like you see quadrilateral or whatever things are there. So you have to do a transformation, right? Isoparametric elements and other things also you have seen. So when you do this mapping, okay, so you may require the derivative also. So what do you call that? What you told is fine only, partial derivative only. What do you call that? A quantity.
Jacobian.
Jacobian, excellent it is. Okay, so that is what Jacobian. So z comma w. So the expression remains the same, no change. Okay, x comma y. But now you have to do this Jacobian actually. Okay, so j x comma y or j. I will write this as j modulus actually. Okay, so this Jacobian say. So generally we can find out like this. Okay, so because dou z by dou x, dou z by dou y, dou w by dou x, dou w by dou y. Okay, or I can also find out in reverse also, that is dou x by dou z, dou x by dou w, dou x y by dou z. Okay, dou y by dou w, inverse basically. Okay, so I can find out the Jacobian this way also, this way also. Okay, so sometimes one of them may be easy actually. So sometimes this may be easy to find, sometimes in some problems, so this may be easy to find. Suppose if this is difficult to say, what you can do is you find out from this method and you take the inverse and then you substitute in the previous expression itself. So this is how we calculate. Now let us say a simple problem say. So z is in a linear transformation. So ax plus by and w. So this is cx plus dy. Okay. And now what will be the density function of zw? Now what will be the Jacobian matrix? So which is easy to calculate here? This way, or you can do this way also. Now, what is a Jacobian here? Tell me. Now, what is a Jacobian matrix? So, if you want to use this one, say, you have to do directly, you can use this one. If I want to use this one, I have to write the expressions, okay, in terms of z plus some, w and y is equal to say sometimes into z plus something into, you followed this w, so you have to invert this expressions also. So anyway, it is a linear transformation. And now tell me this itself, if we use say what will be the Jacobian matrix here? What is it?
ABCD. ABCD.
So it is straightforward case. Okay, so A, B, C, D. So now you know the Jacobian matrix. So you followed it. You have to find out the determinant of the Jacobian modulus turns out to be. So now my PZ, W, Z comma W. So this turns out to be PXY. Okay, and our X is, so we have to write this expression. Let us say write this as capital A, some capital B, some capital C plus capital D say. Okay, so we write like this. So AZ plus B times W, and then CZ say plus D times W, and my Jacobian matrix determinant. So that is AD minus BC. You followed. So this is how we write the the two-dimensional thing. Now let us do very interesting transformation. Say all of you do. Okay, so X Y. Okay, so this is the density function. Okay, now we have a transformation R, which is defined as x square plus y square. Okay, and then we have theta or phi or whatever, tan inverse of y by x actually. Okay, and now I want to find out p r theta r comma theta. So this is what I want to find out actually, knowing x and y. Now what is the physical meaning of this transformation? Now where do we use this type of transformations? So this transformation indicates what? What is the physical meaning of this transformation? X and y I have. R is the square root of x square plus y square. Theta is a tan inverse of y by x.
Cartesian to polar.
Cartesian to polar actual. Okay. So now in Cartesian coordinates, I know the density function. Now I want to find out the same density function in polar coordinates actual. Okay, that is in p r theta this itself. So now as already we told, so our expression is r theta. So r comma whatever this theta is there say. So pxy. Okay, so you have x comma y. And now what will be the Jacobian here? So what is now is you see this problem. So what is the Jacobian matrix? Which one you will use? The first one or the second one? Which is easy here? Dou z by dou x, dou z by dou y. That means it's a dou r by, you followed right? Dou r by dou x, dou r by dou y, then dou theta by dou x, dou theta by dou y you will use, or you can use in the other way around and you take the inverse, that is dou x by dou r, dou x by dou theta, you followed. So dou y by dou r, dou y by dou theta, which is easy to calculate, this one or this derivative? This or this, which is easy. What is the inverse relation? R is x square plus y square. Theta is a tan inverse of y by x. What is, how do you write x? X is equal to and y is equal to. What is the inverse relation?
R sin theta.
R cos theta.
R sin
and
theta.
R sin theta. You followed. Now you tell me which is easier to calculate, this or this? Dou x by dou r is easy to calculate or dou r by dou x is easy to calculate?
Dou x by dou r.
Because it's easy, dou x by dou r is simply cos theta. Dou x by dou theta is simply r into sin theta. You follow, right? So this may be, so it depends. Okay. So if both of them are same only, which one is easy to calculate, you decide. So you can do this way or you can do this way. Okay. So now anyway, this problem, this will be very easy to calculate and you have to take inverse. Okay. That you have to be very careful. Okay. So now, so the my Jacobian say, okay. So this becomes cos theta minus r sin theta, then sin theta, then you see r cos theta. Okay, and I have to do inverse also. So here what will be the Jacobian matrix? Tell me what is the Jacobian here? Cos theta minus r sin theta r cos theta. What's the value? What do you get? Quickly the Jacobian, tell me.
R.
R actually, but you have to do
Inverse.
inverse. So this becomes
1
1
by
by
R.
R. That's it's very easy actually. Okay. So now, so this is our Jacobian. So now my probability R theta, say R comma theta. So I have Pxy. Okay. So X is R cos theta, Y is R sin theta. Okay, divided by, of course, this 1 by R or J will be there. So J is 1 by R. So this becomes, you followed, right? So I substitute this, the determinant actually. So this is how we write. Now in this problem, say, let us say we assume the X and Y, okay? They are normal random variables. Okay, they are normal random variables. And let us say their density function, say, x, y, x comma y is given by this, right, that two-dimensional Gaussian distribution we have already written previously. I will write this as a 2 pi sigma square e to the power of minus x square plus y square by 2 times sigma square. Yeah. So what is your comment when I write, the density function, two-dimensional density function for Gaussian like this? How many parameters were required for 2 dimensions? You remember? What is your comment by looking at this expression? Now, what type of X and Y are what type of random? How many parameters are required for 2D? Now, you remember the whatever we wrote long back? See, two-dimensional Gaussian distribution. So what did we say? Where is that expression? One. No, so this I think we wrote expectation or whatever. Now, this was our two-dimensional Gaussian distribution. Can you see this expression? No. So what did we say? Like this, how many parameters are required for 2 dimensions?
5.
Now, what are those 5? Individual means and then correlation coefficient actual. Okay. Now, when the correlation coefficient was 0, say, what did we say? When correlation coefficient is 0, now what happens to this expression? See, what did we say in the previous class? When Rxy is equal to 0, what did we say? You can write? Now, what is the meaning of this one?
Dependent x and px and py.
Independent only. So that means, px of x is this one, py of y is this expression. So, and of course, you followed it. This is, they are independent only. So now in the present case, say, so now when I write the expression like this in the, in our case right now, so the two-dimensional say, okay. So this the meaning of this. So this sentence you can see this. You can write this as 1 by square root of 2 pi sigma e to the power of x square by 2 sigma square. This is 1. Multiplied by 1 by root of 2 pi sigma e to the power of y square by 2 sigma square. You followed. So this means, so what is this function? So this is a probability density function for x. This is a probability density function for y. Of course, their mean values are 0 and their standard deviations are same itself. Okay. So mean of x, mean of y is 0. Standard deviation of x, standard deviation of y, both of them are sigma, and correlation is 0 actually. You followed. So x and y are normal random variables and they are independent random variables basically. Okay, so this is what we have said. So x and y are independent, the random variables say with the means zeros, standard deviations as sigma, and correlation is also 0. So correlation 0 means obviously they will be independent of the each other actually. And now this is with x and y. Now the question comes, what will be p r theta r comma theta? So this is our the most important question. So what we are trying to say in Cartesian coordinate system, say I am having 2 random variables which are independent of each other. Now I transform to cylindrical coordinate systems here. Now the question comes whether r theta also will be independent or same, or what type of distribution we get for r and theta. Very the fundamental things itself. Okay, and now we will first write the r theta. Okay, r comma theta. So this will be And now Jacobian is one j is this r. So what happens is 1 by r with this our inverse thing will be there 1 by r. So 1 by r if you put r automatically comes into the this one. Okay. So now this becomes r, that is my Jacobian. And now we substitute all other expressions, say 2 pi sigma square. So now we have to substitute r cos theta, then r sin theta. So substitute x is r cos theta, y is also r sin theta, say. So x square plus y square. What happens here? X is equal to r cos theta, y is r sin theta. So what happens to x square plus y square? That becomes
R square.
R square only, because that gets the theta you followed it, that gets cancelled actually. Okay, so finally, so this turns out to be e to the power of minus r square by 2 sigma square. So this is our thing, and here also you have to write the limits. Okay, so the r always lies from 0 to infinity. Of course, this goes from pi to pi or whatever you see. We write these expressions. Okay, so now x and y are independent of each other. Now the question comes whether r and theta are also independent or dependent. So that is a question. Okay, now if independent say, so I should be able to write this expression as pr of r multiplied by p theta of theta. Can I write like this? Is my question, whether r and theta say whether they are also independent or not. So now to do that one, so what you have to do is you have to prove this expression actually. Okay, so now to prove this expression, so you have to find out the probability density function of r, probability density function of theta. Now you know the joint density of r and theta. Now how do we get pr of r and how to calculate p theta of theta? Now, knowing the two-dimensional densities, how do you get one-dimensional quantities? How to calculate individual densities? Now, how do we calculate? We already discussed it. So if I know the two-dimensional densities, px, y, how to calculate px of x, py of y? How to calculate from 2D to one dimension? Is it possible, first of all?
Yeah, it's possible.
How? So how to calculate? How to calculate? Tell me. So previously we have discussed, right, how to calculate this one-dimensional thing.
Using marginal.
Marginal density. Perfect. Okay. So marginal density means what you have to do? PR of r, if I want to find out, say, PR theta this side. What is that I have to do? I have to integrate over. See, this is my 2D. Okay. Now if I have to integrate over what? To get PR of r, I have to integrate over. See, previously we discussed, right? What is that? PR, two-dimensional thing is like row we have, column we have. Now to get row this one, so what is that you have to do? You have to sum over columns. If I want to have this one, so you have to sum over that one. So that summation in the continuous, what do we call this one? So you have to integrate over what to get PR of r? You have to integrate this two-dimension over theta. You followed, right? So if I integrate this over theta, so I will get PR of r. If I want to find out theta, say, what is that I have to do? I have to do the integral over
dr.
Dr actual. Okay, so this you have to be, that's all only you followed. So now here let us do this calculation. So I want to find out PR of r. So of course these are the limits basically. Okay, so 0 obviously we know, so minus pi to pi. Okay, so r by 2 pi, you see, sigma square e to the power of minus r square by 2 sigma square, say, so d theta. So these we have to evaluate this integral. Okay, so now this integral is very easy because there are no theta terms here, so this looks like a constant actual. Okay, so r by 2 pi sigma square e to the power of minus r square by 2 sigma square, pi minus pi will come, so that becomes 2 pi. So 2 pi gets cancelled, so this becomes r by sigma square e to the power of minus r square by 2 sigma square. So this is my probability density function for r. Okay, so this distribution, say in probability theory, we call this distribution is a very famous distribution. It looks like normal, but you have this R which is coming in the numerator. So this we call as Rayleigh distribution. Okay, so Rayleigh, it's a very famous distribution actually. So Rayleigh distribution we call this one. Okay, now this is a PR of R. Now we find out P theta of theta. So now for this you have to integrate PR theta R comma theta say over R. So this we have to do. So now this also the integral you evaluate. So 0 to infinity. So R by 2 pi sigma square. Okay, e to the power of minus R square by 2 sigma square dr actually. Now tell me what is the value. So if I write this expression say, so 1 by 2 pi 0 to infinity R by sigma square e to the power of minus R square by 2 sigma square dr. Now tell me what is the value of this integral. Just use some common sense. It's very easy, the value of this integral. Now what is the value? So the clue is here. Look at the expression for PR of R, and R goes from 0 to infinity. Okay, R by sigma square e to the power of minus R square by 2 sigma square. And now this is the value of this integral. What is the value? Tell me what's the value of this integral. Very easy. Now tell me what's the value of this integral. Guess how much it will be the value. 0 or 0.5 or 1 or 1.52 or what is the value of this integral?
0.5.
0.5. How did you arrive at that one?
I just substituted R square equal to T, R equal to T, means by substituting.
Okay, so you have done some calculations. See, no need to do any calculation actually. What is this quantity inside? What are you integrating? What are you integrating? What is that expression? It is nothing but
PR of R.
now PR of R, if I integrate from 0 to infinity, say, what will happen?
1.
Now why it is 1?
Area under the domain, it should be 1.
Area under the probability density function is
1.
so no need to substitute anything. If you want to substitute also, you will get the same thing only. So anyway, because area under the probability density function is 1, so this becomes simply 1 and 1 by 2 pi actually. Followed. Now you verify this statement. PR of R multiplied by P theta of theta. So now P theta of theta is 1 by 2 pi. Okay. So PR of R is R by sigma square e to the power of R square by 2 sigma square. So this is our, if I multiply these two, I will get this expression. Now what is a PR theta, the original expression? Now you tell me, they are same or different? Now tell me, they are same or different? R by 2 pi sigma square e to, anyway, e to the power of minus R square by 2 sigma square is fine. So this term is fine. 1 by 2 pi is there. Okay. Now here also in the denominator you have a 2 pi. Now what is your comment? Both are same or different?
Both are same.
So what is your comment? Now what is your comment? R and theta are?
Independent, correlated.
They are no correlation, you forget about it. Okay, uncorrelated, that works only for Gaussian. So on R and theta are independent of each other. So now we have said X is independent of Y and they are Gaussian distribution. So automatically when you transform to polar coordinates, still that independence holds. Okay, although the transformation is nonlinear because it is a sine terms, cos terms are involved. Okay, so it's a very important thing. And what is this distribution? 1 by 2 pi. So R is Rayleigh distribution we got. This is 1 by 2 pi. It is a constant actually for theta. So it is a uniform distribution. You followed. So the another most important thing is if I have a Gaussian random variables, uncorrelated Gaussian random variables in Cartesian coordinate system, if I transform to cylindrical coordinate system, I will get Rayleigh distribution and then uniform distribution from the same, the transformation. So this is a very, the important you followed, right? Observation, very important transformation. You can also do for spherical coordinate system. What happens, when you do this type of transformation, like, right, in our mechanics, say, some problems, axisymmetry problems, say, instead of working in Cartesian circular plate or whatever, we try to do it in cylindrical coordinate system. So now when the things are uncertain, loads are uncertain, or things are uncertain, say, so when you want to work in cylindrical, you should know this transformations, okay, axisymmetry problems and others, okay. That's a very important thing. And now let us say one more small thing, which is anyway functions of two random variables it is. So it is nothing but the same thing only. Okay. So we have two random variables, x and then y. Their density function. Now I have one random variable only, z. Okay, which is a function of x comma y. There are no two random variables. Now I just want to find out this much only. Now how do you solve this problem? Now previously you have done y is equal to f of x, we have done. Then x, y, z, w also we have done. 2D to 2D, 1D to 1D. Now we are trying to answer two-dimensional to one-dimensional actual. Now how do you solve this type of a problem? What is the trick we will use to solve these things? So generally in mathematics, when you have these type of things, what is the trick we use? What is the easiest way to solve this one? So you have to do something else, or you can do directly the previous ones itself. Can I use here? So W was not there. If W was there, I can use the previous thing itself. Now here there is no W actual. So what is that? Intelligently, if I want to use this expression itself, say, okay, that is this Jacobian and other things. And now, how do we handle this one? This only I want to use this expression. So this itself can I use here for this problem also, but there is no W here. So how do I write this expression? Tell me, what is the intelligent, what is the thing you can do here? By using the same expression, whatever we have done in the previous problem, I want to solve this problem also. But only thing is there is no W here. Okay. And now how do we handle this? If I want to use the same expressions, I should have two only. But here I am having only one, two are getting mapped to one only. Okay. And now how do we handle this issue? What is the intelligent way of doing things? And what is that you try to do? I want to use the same expression only. This only I want to use, but only problem is W is not there. So how to solve? See, come on, in engineering, we will use lot of tricks. What is the trick you can use here? W is not there. If W was there, I can use the same expression. But now, how do we handle? What is the easiest way? So what do we do in this type of problems? You remember, you can introduce a new auxiliary variable W, which is same as Y itself actually followed. So this is how we do, or you can use W is equal to X itself. So this type of problems, what to do is, so Z is f of X comma Y, I know. But I will write W also is there, but it is same as Y itself. You followed. So now the problem becomes a two-dimension to two-dimensional, but W is an auxiliary variable. It is not like a main kind of thing. So now if I know this transformation, so Z is f of X comma Y, W is Y, or I can even use W is equal to X itself. I can use, the same, the concept itself. Okay. So Px, Y, X comma Y, say, by this Jacobian here. Now solving this, I will get Pz, this W, Z comma W, but there is no W here. So to get Pz of Z, say, so what I will do is I will integrate over W itself. You followed. So then I will get my marginal whatever I have. So this itself is my Pz of Z. So this is a trick, we will try to use it, when you have these type of problems itself. So like quickly, let us see this one. So I have x comma y. Okay. So this is their joint density x, y, x comma y. Now I have a new random variable z, which is x plus y. Now I want to find out pz of z actually. Now what is that I have to do? So this is only, functions of two random variables z. What is the first step I have to do? So I have to introduce it. See, only z is there. Now what is, how do we solve this problem? Just now I told you, right? What is that you have to introduce?
Auxiliary variable.
So which is a w, that is y, or even x also you can take. There is nothing wrong, w is same as y only we take. Now you calculate the Jacobian, say. Okay, so Jacobian, right? Dou z by dou x, dou z by dou y, dou w by dou x, dou w by dou y. So this turns out to 1, 1, 0, 1. Okay, so this is 1 only. So this is my Jacobian matrix. So now my z comma w, say z comma w. So this turns out to be same as pxy x comma y, because my Jacobian is 1, or I have to write the inverse transformation if I do say. So x is, I can write as if y is w, say. So x becomes z minus w. Okay, so z minus w comma w. So this is my the joint, the density function. Now, but I have to find pz of z only, and not, there is no w here. So for this I have to integrate pxy, say z minus w comma w dw. So this integral has to be found out. Now suppose in these problems, if x and y are independent of each other, say. So now what happens if they are independent? What happens to their two-dimensional distribution? If they are independent, see what happens when the things are independent. So the two-dimensional distribution can be written as
in terms of x and y.
In terms of x and y. So I have px z minus w dy of w dw actually. What is this integral known as? Can anybody identify? So it is a special integral z minus w w. Two terms are there. In its structural dynamics, you would have seen this type of integral. What is this integral? See, in dynamics you have done, right? Like, impulse response function you would have done. If I want to find out the response to say x of t for any arbitrary force, you remember what type of integral you use?
Duhamel's.
Duhamel's. What is Duhamel's integral? If f is arbitrary force, say, how do you write that integral? You remember f of tau multiplied by h. See, f of tau will be there. What will be h of? T minus tau d tau. You remember this, right? This expression, the Duhamel's integral. Now compare this with this expression. Whether both, mathematically they are same or different. Instead of a tau and t, say, we are having z and w is there. So this Duhamel's integral is also known as, mathematically, what do we call this integral? Like, f of tau h t minus tau, or z minus w into py of, what do you call these type of integrals? Convolution integral. Excellent. Okay, so this convolution integral, how do you write? So we write generally px of z. This is a symbol we use for convolution. Okay, so py of w. You followed. So this is a symbol we use. So this is also a very important transformation where we have two random variables. Their summation. If I want to do linear summation, say, you have to solve this convolution integral. You followed. So this is also very interesting things comes in probability theory also. Okay, so these integrals, they come everywhere. You followed. Now one other very important transformation we do. This is a most important thing I say. So I am having a random variable u, which is a uniform random variable from 0 to 1, and y is also uniform random variable. Okay, both of them are uniform. So uniform random variable means 0 to 1. Okay, so 0, 1. Now what will be the y value? See what will be the value on the y-axis. So what will be this, 0 to 1. So what will be this value? If it is uniform and if it has to be density function, say, the most important property of density function is? So what's the area under the density function?
Equals to 1.
So 1, so this also should be 1. You followed. So because everything has to be 1. So these are two random variables actual. Okay. So now, so now I have a new random variable set, that is z. Okay. So this transformation is minus 2 times log x. Okay. Whole to the power of half cos of 2 pi y. So this is a very complicated transformation. So z is like this. Okay. So I have x and y, which are uniform random variables. And now I have a transformation, which is a very complicated transformation. It looks to you. Okay. Now we have to find out pz of z. So it's worth doing. So now to solve these problems, you have to introduce auxiliary variable w is y. Okay. Now you find out Jacobian say. Which is slightly difficult because of 2 log x half and other things are there, but you can find out. Okay. So now pz w, z comma w say. So I have a pxy, x comma y divided by this Jacobian. So now this functions, if you calculate, okay. So automatically, you will have some complicated expressions. You do it yourself. So z into some secant square 2 pi w e to the power of minus z secant 2 pi w this entire thing whole square by 2, like that you get, and pz of z say. Okay, so this you have to integrate over because it's a uniform distribution, w is same as y, and y also lies from 0 to 1. Okay, so you integrate this entire expression say. Okay, dw, you will get a nice term like this, 1 by root of 2 pi e to the power of minus z square by 2. So this is the value you get. Now you tell me, what is this density function? What are you getting here? Now what density it is output? Now what is this density function? See this and tell me what type of, what is this density? 1 by root of 2 pi multiplied by e to the power of minus z square by 2. It is?
Gaussian.
It is a Gaussian density. What is the mean value?
Mean
Gaussian
zero. Mean zero, standard deviation 1.
Excellent. Okay, so you get. So what is the very important thing you have observed here? If I have two uniform random variables, say, and if I do some complicated transformation like this, my output can be normal random variable. You followed. So this is a very, very important transformation. So these transformations, they use in computers. If you may be having your computer, no. So how does a computer generates random numbers? You followed in your computer, so there will be some clock, a seed of the random number will be there. So generally all our computers say they can generate uniform random numbers basically. You followed. Now if you want it in MATLAB or any other softwares, you want to generate Gaussian random numbers, some 1,000 random numbers randomly you want to generate, but the probability density function should be a normal distribution, say. So our computer, or if I want to generate chi-square, if I want to generate log normal random variables or whatever, so whatever computer or whatever the codes are there, so what they do is the computer generates uniform only. Okay. Now if I want to generate normal set, they use these type of transformations actual. Okay. So these transformations are very, very important. Even they are coded in computers, and then you follow, right, to generate whatever random number you vary say. They do this transformation. So they generate uniform, and then you have a set of the transformations. Okay, so you can you can generate these random numbers. So you can try, like we already said, no, if you know normal, say if x is normal, you can try now. Okay, what will be x square? What will be the x square distribution of x square? See, if x is normal, chi-square, then what will be e to the power of x? E to the power of x will be what type of distribution it will be?
exponential.
No, no, x is normal. If x is normal, e to the power of x will be be careful, it is not exponential. If x is normal distribution, if I do a transformation, log normal, excellent. Okay. Then you remember, right? T distribution, that is chi-square divided by something else, or all f distribution. All those, if I want to generate log normal random numbers, say, what you will do? You will first, computer doesn't know log normal. Computer can generate only uniform things. Say, I have to do this type of complicated transformation so that I can generate whatever number I like actually. Okay. So this is way which we try to solve, generate random numbers, or do so many things in our practice. Okay. So this anyway. Now the another interesting question is, now let us say x is normal, the random variable. Okay. Now here we are interested in the probability density functions. But generally, as already I told you, right, in practice, nobody wants a probability density function. They are interested only in the movements. Okay. So how movements, how to calculate movements under this transformations. So we are not interested in the probability density. I don't want py of y, because that involves calculating derivatives and all complications are there. I would like to find out just the mean and standard deviation of my y itself. Say, how do we do? Like I have a random variable x, I know its mean value. Okay. Now I have random variable y, which is g of x. Without calculating the probability density function of y through the derivative and others, I am not interested in the density. I just want mu of y and then sigma of y. So how to calculate these type of expressions actually? Okay, directly the movements to movements itself. So can I do this or not? Okay. Now for a simple transformation, so y is ax plus b. So this is our x is mu x sigma x. What will be the mean value of y when for linear transformation? It will be so x is mu of x sigma of x. Y is ax plus b. What is the mean value of y? Tell me. The simple transformation. Yeah. So mean value of x I know, standard deviation of x I know. I want to calculate mean value of y, standard deviation of y. What is the mean value of y? If it is a linear transformation,
A mu x plus b.
A mu x plus, it is just straightforward actually. And what will be sigma y square, the variance of y? No. So what is this variance of y? You remember y minus mu of y whole square. You followed. So what is y? Ax plus b, then mu of y is a times mu of x plus the b, this entire thing whole square, and expectation will be there. So what happens? bb gets cancelled. We have already done, no? A comes out, x minus mu x whole square. So a, I can pull it a outside. So x minus mu of x whole square. What is x minus mu of x whole square? This is nothing but, of course, a square will be there because of square is there. This is what is this quantity? It is nothing but
a square sigma x.
Sigma x square. So without calculating density, without even going into all those calculations, we can do directly movements to movements itself. This also is very the important. So now let us say I have two random variables. Okay, x1 and x2. These are very important transform. And let us say their mean values are mu of x1, mu of x2, and then sigma of x1, and then sigma of x2. There is no, they are uncorrelated or whatever we can say. And now I have a new random variable y, which is a1 times x1 plus a2 times x2. Okay. Now what will be the mean value and others? So this you can. So what will be mean value of y? So you can prove also through mathematically also you can do, or you can do whatever way you like. Okay, so this automatically is a1 times mu x1 plus a2 times mu of x2 and variance of y say, okay, which is sigma square of y. So you prove it, all those details. Okay, expected value y minus mu of y whole square. So you have to substitute all those terms. Tell me what do we get finally? Can any of you calculate? See, y1 is a1 times x1 plus a2 times x2 minus, so a1 times mu of x1 plus a2 times mu of x2. So you have to do these all the calculations. So if you do all the things, finally you will get a1 square sigma x1 square plus a2 square sigma x2 square plus 2 times a1 a2 sigma x1 x2 actual. So you have this joint thing also. Suppose if it is 0, say, then it will be a1 square plus a2 square. This only terms will be there. But if there are some correlations, and if you know their the joint at the covariance or whatever, then this expression comes into picture actually. Okay, so this is a very important transformation. The linear regression, whatever you do, say, suppose if you are doing multiple random variables, linear regression. Essentially, linear regression you will do like this. Okay, so we have several random variables up to some xn, and let us say y is I is equal to say 1 to n ai into xi. Okay, so now the mean value. So mean value of y will be I is equal to 1 to n ai mu of xi. So this will be the mean value, and then the variance of y, say sigma I is equal to 1 to n ai square sigma xi square plus you have the covariance term also comes into picture, because now you will be having several random variables, no? So you will be having several covariance of xi comma xj, and of course I is not equal to j, because when I is equal to j, obviously this term comes into picture. So this is how we handle, you see, the multiple the random variable, and these are very important in solving linear regressions, or when there is a summation, say. Okay, so you can solve the many problems through this expressions itself. Okay, so this way you can find out the things like the transformations, so movements to movements or probability densities to densities, so you can calculate through all these type of expressions itself. Okay, so fine. So anyway, I will stop here, so we'll continue in our next class. So if you have any questions, you please ask. Yes.